Okay, thank you. It's a great pleasure and honor to be invited here to talk about the mathematical legacy of Vladimir Voevodsky, and to hear all the many diverse things people are talking about to honor that. So I gave an abstract to this that was probably a little off-putting, and I am going to talk about what I wrote in there, which are even spaces and some results in homotopy theory that would have an impact on some problems in algebraic geometry, but I'm only going to get to this at the very end. So one of the things that Vladimir did, is in his work on the Milnor conjecture, he connected this elaborate apparatus of homotopy theory to problems in algebraic geometry in a very profound way. And in homotopy type theory, he also made a deep connection between constructs in homotopy theory and constructions in the foundations of mathematics. And there's a lot of things that come out of great mathematical insights. Sometimes out of an insight like that, you get a trick that tells you how to solve a problem. And sometimes you create a connection between two areas in math that really bring radically different intuitions to the same question. Like in algebraic geometry, you think in the 70s there was the beginning of this exploitation of, you could take a problem in algebraic geometry over the complex numbers, realize it over a number field, reduce mod p, and study Frobenius acting. And you'd have completely different intuitions than you might get from complex analysis. And in terms of eigenvalues of Frobenius, once counting points on curves became connected to coding theory, people in coding theory brought radically different intuitions to the distributions of eigenvalues of Frobenius and problems in number theory. And with quantum computing, the insights that come from quantum information theory and information theory have given us new ways of understanding just basic quantum mechanics. And Vladimir, he really managed to do this twice. And I want to talk about the impact of his ideas on algebraic topology and how these allow one to bring really different intuitions to questions, basic questions in algebraic geometry. So the first thing is that during a little bit of historical stuff, the development of algebraic topology kind of was in concert with the development of algebraic geometry and the theory of manifolds. But many problems in mathematics were understood. It came because many problems were understood to be problems in homotopy theory. And this was due in large measure to the fact that bundle theory is homotopy invariant. A bundle over a space across an interval is constant in the interval. A one-parameter family of bundles is actually isomorphic to a constant one. And I was giving a talk on this stuff in Mexico last December, and John Milnor was there. This is the same Milnor that wrote down, there is only one Milnor, but Milnor wrote down some of the first constructions of universal bundles and made the Milnor conjectures. And I was asking him, when was it recognized that bundle theory was homotopy invariant? And he thought for a minute and he said he didn't know. This was really already part of the woodwork when he was a student. It was well in Steenrod's mind that this was the case, and he didn't know. And then out of the blue, he stopped and he said, but the real revolution that I remember was when we went from writing down maps in terms of commutative diagrams. And he said it used to be that you had to write these really convoluted expressions, and this made the depiction of identities between maps something much easier to explain. And I was struck at the time, and I went back, and it made me do the exercise of taking some complicated diagrams and writing them down in terms of equations among maps. And they just look like something a machine would do. There's no meaning in them. And I was thinking about this over the course of this conference, how this little observation, it really is sort of represents the theme, the two themes that are alive at this conference, this connection between the homotopy theory, invariance of bundles, and all the impact that had on algebraic geometry, and this theme in terms of univalent foundations, and really like directly into André Joyal's talk, where he talked about these computers finding these proofs of the Blakers-Massey theorem, presumably unencumbered by our need for semantic meaning in these symbols. So I don't know, that sometimes when I face these amazing coincidences, it makes me think, this is just an affirmation that we're all beings in one great universe, and the things that divide us are an illusion, and whether by entropy or a spirit in the sky, all beings are part of one great being. But sometimes when I encounter things like that, I think, what did they just run out of memory? This is just further proof that we're living in a simulation. So I don't know which, but anyway, these themes of Vladimir's, that they seem somehow universal. All right, so today, thanks in large measure to Vladimir, many problems in mathematics are being seen as having a homotopy theoretic aspect, and this is largely due to his work with Fabian, using abstract homotopy theory to set up the world of algebraic geometry in a way that we could investigate through the means of homotopy theory. Okay, so the question I want to think about, I want to address is which complex vector bundles on complex algebraic varieties have an algebraic structure? Now, this is a very hard question. If you could answer this question, you could solve the Hodge conjecture. And I'm not going to solve the Hodge conjecture today, but I just want to indicate this is a question that's been intensely investigated by many mathematicians. And in the 1970s, Phil Griffiths undertook to investigate the Hodge conjecture by investigating when complex vector bundles had algebraic structures. And his approach...
What do you mean by complex vector bundles?
I mean, just a...
Topological?
Yeah, topological.
Okay.
Yeah, topological complex vector bundle. So by a result of Grauer on an affine, smooth affine variety, such a vector bundle has a holomorphic connection, and Griffiths was trying to study the growth rate of that connection using value distribution theory and the methods of complex analysis. But this work of Morel and Voevodsky lets us approach this question using the methods of homotopy theory. And this is an example of something where you have really radically different points of view on this same problem. So what do the methods of homotopy theory look like? Well, one of the keynote things in homotopy theory is homotopy groups, which are maps of spheres to spaces, and then the way we might manufacture spaces out of homotopy groups by forming cell decompositions. Here's a picture of a cell decomposition, a space, maybe a torus, that's broken up into much smaller and simpler pieces. The methods in homotopy theory tend to be very internal to the subject, and they involve spaces designed to have good homotopy theoretic properties, but not very accessible geometric properties. And here's just a list of some of the terms that we use all the time that kind of have often barely made it outside the world of algebraic topology. All right, well, that's a long wind-up. Let me get down to some very concrete examples of what I'm talking about. And the first thing is I want to think about vector bundles over projective space. So I'm imagining projective space of dimension n over the complex numbers with homogeneous coordinates I'll indicate with xi, and O of d, the standard line bundle whose sections are homogeneous rational functions of degree d. So the first thing the most elementary example to look for the homotopy invariance of bundle theory and to see if it's possible to access this with homotopy theory is on the projective line, and to look at the bundles O of 1 plus O of minus 1 and the trivial two-dimensional bundle. Now, these are not isomorphic. There's no polynomials of degree -1, so there's no maps from the trivial bundle to O of minus 1, but there's a one-dimensional space of maps from the vector bundle on the left to O of minus 1. So, however, these vector bundles, topology tells me they should be isomorphic. The only topological invariant we have of these is the first Chern class, and that they are the same, so topologically they're the same. And we can remedy this in algebra by adding two more quantities, y0 and y1, whose dot product with x0, x1 is 1, and then write down an isomorphism. Now this doesn't change the problem in topology, because the difference between any two solutions to that equation is a solution of the homogeneous equation x0 y1 plus x1 y1 equals 0, and that's a vector space. So the space of these pairs x, y is homotopy equivalent to P1. And one thing this points out right away is that the theory of algebraic vector bundles, just taken naively, is not a homotopy invariant problem. These two bundles are not isomorphic over P1, but they are isomorphic over something algebraically homotopy equivalent to it. So I set that up to make that point, that the bundle theory, just as given, isn't really homotopy invariant. But I also wanted to introduce this really cool thing called Joannolu's device. So Joannolu's device is a homotopy approximation to any well, let's say quasi-projective variety. And in the case of projective space, the thing I showed you is an example of the Joannolu device. And for projective n space, instead of looking at the space of lines to the origin, you look at the space of rank 1 projection operators. That's a smooth affine variety that, for the exact same reason I described in the case of P1, is homotopy equivalent in the algebraic sense to projective n space. Okay, so I already mentioned that. But the reason that of these two bundles weren't isomorphic had to do with the fact that sequences of bundles on projective varieties don't necessarily split, and they do in topology. But they also do on affine varieties, and this makes you wonder, maybe the theory of vector bundles is homotopy invariant. Maybe bundle theory is homotopy invariant in the case of affine varieties. Okay, so I want to do one more example, and I want to do this because there's something in here I found really hard to solve, an algebraic formula I found hard to get. And I guess since I said that, I hope it really is hard, otherwise maybe I was working hard for nothing. But I want to show you this formula to indicate that in topology, there can be something that looks obvious from the point of view of topology that seems really mysterious from the point of view of algebra. And this is an indication that you are really bringing radically different visions to radically different meaning to some of these structures one's investigating. So let's look on the projective plane and take the ideal that defines the point 0, 0, 1, say the point at infinity. Then that ideal is locally generated by two elements, say the coordinates x0, x1, and if you set it up a little more carefully, you'll see that there's actually a vector bundle, a two-dimensional vector bundle that gives you a presentation of this ideal. Now, this two-dimensional vector bundle, it has a non-trivial map from O of 1, so it can't be the trivial bundle. On the other hand, if you go and calculate its Chern classes, you'll find they're 0, and on a rank 2 bundle over the projective plane, that's the only thing that topology can see that makes it non-trivial. And the question is this bundle trivial back on the space of rank 1 projection operators? And it is. It turns out to be the case, and I'll explain a bit later that we actually know this a priori. But what you have to do to trivialize it is show that over that ring, the ideal generated by x0 and x1 is generated by two elements of degree -1. And that's something I found to be a somewhat non-trivial problem. I'm going to put the answer up, not because I want you to process the answer, but in hopes that someone in here who's way better at thinking about these things might be able to tell me how one looks at the world so that finding an answer like this is obvious. So anyway, this is a lot to process, but you basically take the defining equation and square it to extract these quantities R, S, and T, and then you take a sum of this rank 1 matrix and this skew symmetric matrix and multiply it by the variables x0, x1, and then you get these two generators. Okay, so this wasn't meant for you to process unless it's easy and for you, in which case tell me. It's meant to show you that there's something that topology is predicting in the algebra that is really, really difficult to see from the point of view of algebra. Okay, so this leads to some questions. Like, so far, in the two examples I've shown you, topologically trivial bundles on this Jn look like they might always be algebraically trivial. You can do analogs of this in dimension 3. In dimension 4, it's conjectured, in 4 and higher, it's conjectured that the only topologically trivial algebraic vector bundles on Pn are already trivial. So, but that's an open problem. And, well, anyway. But we might ask, in the affine case, where bundle theory is homotopy invariant, is there a difference between algebraic vector bundles and topological vector bundles on this affine approximation to projective space? All right. Sorry, I'm having an equipment malfunction.
Griffith's growth conditions would be satisfied, perhaps.
Yes, yeah, right. Okay, oops. So I wanted to get into, so I want to talk a little bit about the history of investigating the homotopy invariance of bundle theory in algebraic geometry. So this starts in Serre's famous paper on algebraic coherent sheaves, where he exploits and probably invents this analogy between vector bundles on a space and finitely generated projective modules over the ring of functions. And he certainly has in mind the homotopy invariance of bundle theory, and he states in this paper that when X is affine R space, so that the ring of functions on X is a polynomial ring, it's not known if there exists non-trivial vector bundles. In topology, they're all trivial, and he remarks that this is not known. So this is just a remark, and I guess part of Serre's karma is that when he made a remark, it turned into Serre's conjecture. This was eventually solved in the 1970s independently, but almost simultaneously by Quillen and Suslin. And they both showed that, in fact, finitely generated projective modules over polynomial rings over a field are free. And this was the beginning of this idea that bundle theory might be, on affine varieties, might be something homotopy invariant and accessible to the methods of homotopy theory. So then Bass and Quillen later made that conjecture, that if you have a commutative regular ring of finite Kroll dimension, then bundle theory, the theory of vector bundles over the spectrum of that ring, is homotopy invariant. And this was proved in the case when the smooth algebra, the smooth variety, was finitely generated over a field. And this is called the geometric case. And this theorem of Lindel's, which is largely exploiting the methods of Quillen and Suslin, really opened the door to this idea that this might be a problem in some kind of homotopy theory. There's a beautiful book on this story by T.Y. Lamb called Serre's Problem on Projective Modules, if you decide you want to get more interested in this. Okay, so this is supposed to be a problem in homotopy theory, but what kind of homotopy theory? And And I want to talk about three different kinds. And really, we owe the fact that we can do this to Voevodsky. I mean, abstract homotopy theory was something that was just around, very internal to algebraic topology until about the 1990s when Morel and Voevodsky wrote their paper on the homotopy theory of schemes, and Vladimir used spectacular and sophisticated methods to solve the Milnor conjecture. And after that time, people in a much broader community started absorbing abstract homotopy theory, and now it's used in all kinds of places. So I want to be very brief. The way I like to present these is you start with some category and a bunch of maps that you want to regard as equivalences, and you localize at those equivalences, or you study things systematically that are invariant of those weak equivalences. So if I started with topological spaces and ordinary homotopy equivalences, that's classical homotopy theory, and I'll indicate that with the symbol top. The first version of algebraic homotopy theory, the homotopy theory for algebras, was done by Ken Brown in his thesis called Abstract Homotopy Theory and Generalized Sheaf Cohomology. And Ken wanted to have available in algebraic geometry a representing object for sheaf cohomology. So he wanted to make Eilenberg-MacLane spaces for sheaf cohomology. And in this case, the category was smooth varieties, or the category of simplicial presheaves on smooth varieties. And he considered Zariski and the étale topology, but nowadays, I mean, you could also do this with the Nisnevich topology. So you're just looking at simplicial sheaves that are Nisnevich sheaves. And this gives you some kind of algebraic homotopy theory. And this is a very formal thing. You don't get a lot of new insights about specific calculations, as you'll see later, from this kind of homotopy theory. And what Morel and Voevodsky did was they added to the notion of equivalence the idea that the affine line should be contractible. So you set up a world in which you're systematically studying algebraically homotopy invariant things. And this is Motivic homotopy theory. And it's an extraordinarily rich world. I learned a lot about it from Vladimir and a lot more about it from Fabian. Okay, so that's Motivic homotopy theory. So there's some forgetful functors. You can go from a problem in algebra to a problem in Motivic homotopy theory to a problem in topology. And we can study vector bundles in these categories. So in topology, as Fabian mentioned in his talk, vector bundles are homotopy classes of maps into the classifying space of the general linear group. You can look at the exact same thing in, sorry, I think I'm going to have to give up on this. You can look at the exact same thing in algebraic homotopy theory. So I think I skipped a slide by accident. That's up on the right. And in that case, the fact that algebraic vector bundles are homotopy classes of maps into BGL, that's not a deep fact in that category. That just recovers the description of vector bundles as H1 with GLK coefficients. So there's a third object we can study, which I like to call motivic vector bundles, which is whatever is classified by maps in motivic homotopy theory to the infinite Grassmannian, or the classifying space of the general linear group GLK. And there's realization maps, there's forgetful maps between all of these. And so the question, does a topological vector bundle have an algebraic structure, is can something here be lifted all the way to here? And one can try to break this problem into two by lifting it to motivic homotopy theory and from there to algebra. Now, this theorem, this is a really fantastic theorem, and this is really the ultimate expression of the homotopy theory invariance of bundle theory in algebra. And Fabian mentioned this theorem in his talk. I wrote the date 2012 because that's when he published the result in his book, but I know from personal conversations it was around for a long time before that. There was a dramatic simplification and a generalization of this in 2015 due to Aravind Azak, Mark Oiwa, and Matthias Wendt. And their approach is so close to the foundations of the subject that I think you can really start learning motivic homotopy theory nowadays by aiming for this theorem. And I think Aravind has even done that in a graduate class. So if you're trying to get into this subject, this is actually a pretty reasonable theorem to aim for. And as I said, it's the foundation of what allows the homotopy theoretic investigation of bundle theory. So yeah, I wanted to really cement that. This is the affine homotopy invariance of algebraic bundle theory. Okay, now, what does this buy you? What does sort of having bundle theory be homotopy invariant in a different category buy for you? It buys obstruction theory. So remember when I had that slide up about all these different, the internal methods of algebraic topology, and one of them had to do with taking a space apart into cells and recovering it, taking a space apart into simpler pieces. And what happens is anytime you're doing abstract homotopy theory, there's a kind of cohomology and a kind of homotopy and a relationship between homotopy classes of maps from X to Y and the cohomology of X with coefficients in the homotopy groups of Y. But what cohomology and what homotopy groups mean, it radically changes in the category you're in. So in algebraic homotopy theory, the classifying space of GLK only has two homotopy groups, and this obstruction theory just reduces to what you could take as the definition of vect K of X. So the algebraic homotopy theory, that's the sense in which it's formal. It's not decomposing the homotopy type of the classifying space of vector bundles into pieces any finer than what you knew when you made the definition. But the Morel-Voevodsky Motivic homotopy theory makes a radical change. It radically changes it allows you to radically penetrate the homotopy type in a really different way. So the fundamental group of BGLK is GL1. So the homotopy groups are not abelian groups. They're special kinds of abelian sheaves on the Nisnevich site. And pi 2 of BGL2 is mod 2 Milnor-Witt K theory. So if you just step back right now and you think about what does this mean we can relate, I don't know how to do this, but in some sense there's a relation. This is saying there's a relationship between value distribution theory on a holomorphic connection on a complex vector bundle and things like Steenrod operations on mod 2 Milnor-Witt K theory and completely different kinds of algebraic objects. I don't know the relationship between these. It's on my to-do list. Sorry, but and maybe we won't see a good relationship. But this is the gift of this point of view. It really does bring these radically different points of view together on the same problem. So this has been used a lot. So Fabian, Morel, and Azak and Fazl have investigated splitting free summands off projective modules over regular rings and classifying projective modules over smooth algebras of Kroll dimension less than or equal to 3. Jean and Aravind and I got interested in, so the mission in the 70s investigating this problem was to solve the Hodge conjecture. And so the idea, what they were trying to get were the Chern classes of a topological vector bundle were algebraic. And there's a spirit, it's not stated, and probably if cornered no one would have believed it, but there's a spirit in this literature that if the Chern classes are algebraic, that's probably the only obstruction to the bundle having an algebraic structure. So Jean and Aravind and I started using these methods, and we found an example of a of a rank 2 vector bundle over a smooth threefold, affine threefold that has algebraic Chern classes, but which there's a more subtle obstruction to having the bundle have an algebraic structure. So these are very powerful methods, and they give you invariants that you wouldn't know how to look at from other points of view. Okay, so I started out motivating this whole discussion by talking about topologically trivial bundles, and now I want to talk about some interesting non-trivial bundles that look like they would be very hard to understand from the point of view of algebra. And these were first written down by Elmer Rees in the 1970s. So what are these? Well, the topological vector bundles, these are rank 2 topological vector bundles over a complex projective space. So those are maps from projective space into the classifying space of the 2x2 unitary group. And the obstruction theory relates the cohomology of projective space, the homotopy groups of the classifying space in the unitary group, and rank 2 bundles. Now, for I bigger than 1, pi 2I of the classifying space of the unitary group is pi 2 minus 1 of the 3 sphere. So if you're interested topologically in rank 2 vector bundles on a complex projective space, you're interested in the odd homotopy groups of the 3 sphere. Well, maybe I don't want to know all of them. Maybe I just want to know where's the first one. And that was found by Sayre. And the first non-zero odd homotopy group of the 3 sphere, localized at a prime p, is in pi 4p minus 3 of S3. And so that corresponds to a vector bundle over the complex projective space of dimension 2p minus 1. P is a prime now. And that's the map classifying it. It uses this particular element in the homotopy groups of spheres. And Elmer Rees showed that bundle was non-trivial. He worked out to which higher projective spaces does it extend. And by construction, the bundle has no Chern classes. So when Elmer proved this theorem, there was another paper. Oh, so it has no Chern classes, so it's unstable in the Mumford sense.
Why does it have no Chern?
Because it factored through, the classifying map factored through that sphere, which will have dimension greater than 4. And so when Elmer did this, it was in response to a prospect in algebraic geometry. There was a theorem of Grauer and Schneider, which later turned out to have a famous mistake, that said that in dimension greater than or equal to 4, unstable vector bundles that an unstable vector bundle could not have an algebraic structure. And so this was introduced. It was supposed to be the first, and so the vanishing of the Chern classes implies that it's unstable. And this was supposed to be the first example of a rank 2 vector bundle on a complex projective space with no algebraic structure. So that paper turned out to have a mistake, and to this day nobody knows if there are rank 2 algebraic vector bundles on projective space with no algebraic structure. It's a completely open problem still. Okay, so that has no Chern classes. Let's see.
You switched to the projective right from the affine maps now.
Yeah, I was just telling you that for historical interest. I can't. The methods of Motivic homotopy theory rely on the homotopy invariance of bundle theory, so I can address this question over the affine approximation. And I'm going to look at that. Now, then there would be a problem of descent from Joannalou's device to projective space, which seems to be, maybe that's as hard as the original problem. That seems to be tricky. All right, so here's the question. Do the Rees bundles exist over this space of rank 1 projection operators? As algebraic vector bundles, thank you, yeah, Oh, so the answer is yes. So that's a theorem of Aravind Azak, Jean Fazel, and myself. And I want to tell you a little bit about that, but before I do so, let me just step back and tell you what this gives you in algebra. it tells you if you study, so this bundle is rank 2. If you add a trivial bundle, it'll be trivial. And that tells you that this bundle is the kernel of a map given by a 3x1 matrix, or 1x3 matrix, a unimodular row over the degree 0 part of that ring. There's 3 elements in that ring that generate the unit ideal, and the kernel of that is this rank 2 bundle. The method that produces these is so different from the things you can bring to bear on a problem in algebra that we have no idea what A, B, and C are. And even if you did have that idea, the methods that prove that this projective bundle is not free are also so far from anything I would know how to write in algebra. I wouldn't know how I wouldn't know an algebraic method to show that this projective module is not free. So this is, in a way, it's a very striking example of what I said at the beginning, that creating this opportunity to bring these radically different intuitions on these problems in algebra is
So it's not free because it's topologically not
exactly
not trivial.
right. But the thing that
That's the point.
yes, exactly, and the thing that detects it in topology is it's way up there. It's hard to access in algebra. Okay, so. Right, so the construction of the Motivic Rees bundles. So I have to look at the clock. I have to look at the clock for a minute. I'm either going to have to tell you that it's extremely difficult, and the only way to really understand these Rees bundles is to have spent 10 years training at a remote Himalayan dojo in the martial arts and meditation, and maybe then you could understand it. But I seem to have like way more than 15 minutes left. So I think I'm gonna go for it a little bit because I want to illustrate. In a way, I think what I said made the point, but I want to maybe this. I've prepared some slides on this, and I think maybe this will illustrate a little bit what these different techniques are. So let me draw a diagram first of all. So that's this triangle at the top. So this map from GLNC to the 2n-1 sphere just takes a matrix and looks at its top row. And there's a map that doesn't have a section, but if you multiply that by n-1 factorial, it does. So this is just a shifted around, this is a theorem of Bott. You take the generating vector bundle over S2n, and you look at its nth Chern class, and Bott proved that that's n-1 factorial. And if you translate that into the information about clutching functions, you get this. Okay, so by some standard methods in homotopy theory, which I won't describe for you, that have analogs in algebra, that leads to a map from the 2p sphere to the 3 sphere, and you can compose it with its suspension and get this other map. Now, we want to imitate this in motivic homotopy theory. And so the first thing I have to tell you about in motivic homotopy theory is what spheres are. So now, in motivic homotopy theory, there are two kinds of spheres. There's 2 indices. You can think of one as the classical topological dimension, and the other measuring what's called the Hodge weight, or measuring kind of how much algebraic geometry it's seeing. So the affine line, I can remember Vladimir drawing these pictures. If you take the affine line and you think of that as the complex plane and remove the origin, you get something you want to think of as a circle, or the 1 sphere. Or you could also take the affine line and glue 0 and 1 together, and you'll get a different circle. And then by combining these, you can get a sphere, a PQ sphere for every P and every Q. And the thing that's relevant to us is that Pn mod Pn-1, which in topology is just the 2n sphere, has Hodge weight n, and the affine n space minus the origin also has Hodge weight n, but the dimension 2n-1. And then there are homotopy groups that are doubly indexed as well. so I think I've already motivated this. Why don't we skip that explanation there? And let me go back to this key diagram. So I could take the general linear group and I could still look at its first row, and that gives me a map to affine n space minus the origin. And I want to take this map, this n minus 1 factorial map, and lift it through GLN. So this is a specific problem in algebra. I would have to work over this Joannolu device, but it's asking that if I have a unimodular row, can I complete that over a ring? Can I complete that to an n by n invertible matrix? Now, this is an interesting situation. So in topology, this has to do, in topology, this has to do with the first Chern class of the generating vector bundle over S2n. And there is an algebraic formula for that given by Clifford algebras. It's written down in Atiyah, Botten, and Shapiro. And that gives you a vector bundle of dimension 2 to the n. And we need a vector bundle of dimension n. And in principle, you should be able to, and it row reduce the clutching functions to get an n by n matrix. But this is one of these weird problems in algebra. If you try to do that, you're going to fail because it's one of those problems that a greedy algorithm won't work. You can't get there by making it look easier at every step. At some point, you have to make it look a lot harder. So amazingly, Suslin did this. There's a I think this was even in his thesis. It's called Suslin's unimodular rows, or his n factorial theorem. And he constructed this lift algebraically. So the very starting point that gives you this very first map is provided for us in algebra with this very beautiful theory of Suslin. And it seems to have escaped, oh no, I think this is here. So that gives us this diagram, but in order for that map to have degree n minus 1 factorial, I need minus 1 to be a sum of squares, which over the complex numbers it is. Okay, so now you do some things, and in topology, you get a map from S4p minus 3 to the 3 sphere. If you do the things in topology, now these maneuvers in topology they're algebraic, but it's very difficult to keep track of the information you would need to make a projective module out of this step. But there's an even worse step. What did I really need if I wanted to make this vector bundle? I needed a map from a quotient of a projective space by a lower one to a sphere and into BGL2. And so what I didn't need a map from the 4p minus 3 sphere with this Hodge weight to this sphere. I needed it with that Hodge weight. And so the Hodge weight is wrong. Now, if you're swaying with the homotopy groups of spheres and you start thinking about where am I going to see in this world the failure of a topological vector bundle to become algebraic, this is the best place. You're going to hope that you did some elaborate calculation to learn about this element in the homotopy groups of spheres, and the Hodge weight was wrong, and you can't fix it. And then you're going to go back and try to reverse engineer that into some sort of obstruction to the existence of the bundle. But in Motivic homotopy theory, there's an operation that lowers the Hodge weight on the torsion. I think I won't describe that, but that means that the only way something could go wrong is if you produce something whose Hodge weight was too low, and we produced something whose Hodge weight was too high. And the construction, the Suslin matrices or whatever, shows that that element is killed by p, so you can multiply it by this operation that changes the Hodge weight and lift the Rees bundles to Motivic bundles. So that's the flavor of it. I've done a lot more of this. Let's see, I think I already said this, but I'll just leave this up while I speechify a little bit. I've done a lot more of these calculations, and with John and Arvind, and we can't find any bundle that we can make in homotopy theory that we can't lift to the Joannolu device, to Motivic homotopy theory. There's a big list that was compiled by Switzer of rank 2 bundles over projective spaces in a big range of dimensions, and we haven't gone through that whole list, but it looks hard to find counterexamples. And this makes you think, is the restriction map from algebraic vector bundles over Jn to topological vector bundles over projective space a bijection? Is it possible that there really is no difference between, that the Griffiths obstructions just don't exist in this case, and there's no difference between these? So I want to, they have the same homotopy type. I could put Jn on the right, and then everyone would have to remember what Jn is. But yeah, I could do that. Yeah. Yeah.
And that's the question you're studying. You're studying over an affine variety, whether B algebraic equals B motivic.
Yeah, yeah. And I'm over something.
The question you've been discussing.
Yeah. And I'm over projective n space, so I'm every integer cohomology class is algebraic, so I'm as far from the Hodge conjecture as I can be. And this is somehow saying, you know, it's sort of this idea, the idea that this is true would be some vector bundle analog of this property of projective space, that the integer cohomology classes are all of Hodge type and they're all algebraic. So I want to explain a philosophy and how one can use some really deep theorems in homotopy theory to approach this, and why I think this is probably true. But I'm not announcing a theorem that it's true. So for topological vector bundles, you know, you're looking at maps of you're looking at the homotopy groups of the 3-sphere. And so you're not going to compute all of those. So you need to take some machine that does compute those for you and hope that the Motivic analog of that machine produces the same calculation. And the useful machine for this is something called the Adams-Novikov spectral sequence, or the unstable Adams-Novikov resolution. So you start with the complex cobordism spectrum. This appeared briefly in Fabian's talk. I don't know if that gives me license to talk about it, but the complex cobordism spectrum it's some kind of moduli space of complex manifolds moving through cobordism, and it represents a generalized homology theory, and that can be used to try to calculate homotopy groups. Okay, so that's the method, and there's a favorable, in certain circumstances, this resolution works out in an extraordinarily favorable way in algebraic topology, and it looks like it also does that in Motivic homotopy theory, and if it does, then one can probably show that all topological vector bundles lift to algebraic vector bundles on J. Okay, so we call this the Wilson space hypothesis, and it's based on a really amazing theorem of Steve Wilson. So in algebraic topology, there's a lot of naturally occurring spaces that have cell decompositions with only even dimensional cells, like complex projective spaces, Grassmannians, the state spaces of completely integrable Hamiltonian systems. There's just a huge, anything that, more or less anything that comes to you with a natural algebraic torus action tends to have a cell decomposition with only even dimensional cells. So I'm going to call those homologically even spaces. And for a homologically even space, the odd homology groups are 0, and the even ones are free abelian groups. So there's an analog of this in homotopy theory, for homotopy groups. So a space will be called homotopically even if its odd homotopy groups are 0, and the even homotopy groups are free abelian. And Wilson defined a space to be an even space if it's both homologically and homotopically even. Now, this is difficult to achieve, and the only commonly known examples are infinite dimensional complex projective space, the classifying space of the infinite unitary group, and the classifying space of the infinite special unitary group. And those last two we know are homotopically even because of Bott periodicity. And the amazing thing Steve Wilson proved is that the classifying spaces for complex cobordism, for the even spaces in the complex cobordism spectra, are even. And that means that if X is homologically even, so is this space. And then
C's are around the infinite loop space of MU.
yeah, the last functor applied is the, okay, so in this notation, that's loop infinity parentheses mu smash x, and now I want to think of that as a functor of x and iterate it, and that's what that notation there means. But the Wilson space hypothesis means that if x starts out homologically even, you never leave the class of homologically even spaces when you do this. And in fact, not only are these homologically even, these are even. And that means they, by their condition on homotopy groups, can in turn have resolutions by kz2n. And that's a very favorable circumstance. And I wouldn't know how to make these resolutions without Wilson's theorem, but it gives you a way of decomposing a homologically even space into particularly nice Eilenberg-MacLane spaces. All right. So one can make an analog of this in Motivic homotopy. And I think since time is getting short, I'll just, and the notes will be available somewhere. There's an analog of this in Motivic homotopy theory, suitably formulated, and the Wilson space hypothesis is the analog in Motivic homotopy theory of the one in algebraic topology. Now,
and the homotopy is not at all, it's the homology. Right?
Exactly, yeah. These are known to be homotopically even, and it's the homology that you don't know. Right. So is the motive pure Tate? Right. That's what you're asking. And why would one suspect this? Well, it's not. Wilson's proof is it's an elaborate inductive calculation using a tool for the induction that's not available in Motivic homotopy theory. But if you think about, so the connection between homotopy groups and manifolds comes via the Pontryagin-Thom construction. If I have a complex manifold or maybe a cobordism between them, I don't just immediately get an element in the homotopy groups of this spectrum. I have to embed it in a big Euclidean space, a big complex vector space, and then use Pontryagin-Thom to make the map. So these classifying spaces, there's a lot of ways of describing a homotopy type, but they probably shouldn't be thought of as bare manifolds moving through cobordism. They're manifolds sitting inside a big complex vector space. And that complex vector space, that's a contractible choice, but it affects the way you think geometrically about the model for these moduli spaces. And that complex vector space has a big complex torus action. And for instance, it should remind you, like in D for dimension 0, of the Hilbert scheme of points in the plane. And I think what we're hoping is that there's a kind of Hilbert scheme style model, some sort of end Hilbert scheme model for these spaces that provides them with a good enough complex torus action to make them even. But that's a pipe dream. Well, I don't know. There's quite a few people working on that now, but there's a reason to think this might be true. Okay, so if the Wilson space hypothesis is true, and if what Fabian was mentioning in his talk about the HZ complete, that the classifying space of GLK is HZ complete, there are enough other theorems around to show that that the map from algebraic vector bundles over this Joannolu device to topological vector bundles over projective space is a bijection. So it was no accident that we could lift the Rees bundles. It's true of all bundles. So that depends on these two somewhat tricky things, but they're things one would want to know about anyway in motivic homotopy. So there's another piece of evidence here that Mike Hill and I investigated the analog of this in. So there's a question about field of definition. You know, should the Wilson space hypothesis be true over the reals? Should it be true over Z? And there's a reality check. If it's true over the reals, it has to be true over when you let what's called real boardism, when you let the Z2 act by complex conjugation on complex cobordism. And I didn't give you the apparatus of definitions, but Mike Hill and I, just a couple of months ago, posted a paper to the archive giving a proof that this is true in real homotopy theory. And there's many other situations where we're able to prove it's true. It seems to be kind of a ubiquitous result, and it really does seem to suggest that the Wilson's theorem should be true for a geometric reason and not because of some calculation. Okay, well that's kind of the arc of my talk. I wanted to end 2 days ago. A friend of mine sent me a picture. I edited it slightly. And I know in my heart that this can't be real, but I take comfort in thinking of this as some kind of a sighting. But I don't know. I just want to leave you with that picture. So, thank you.